Good evening, everyone. I'm here to tell you a story. That's what we do in geology, we tell stories. But this story is a bit about not merely interpreting the data we collected, but it's how we were able to collect the data. I have a mantra about cruises. My mantra is, I'd rather be lucky than good. On this cruise, to navigate, literally, all the obstacles we encountered, we were incredibly lucky to be able to sail away from the pier in Nome. Regretfully, our luck ran out when we encountered the ice edge. The ice this year was more extensive and thicker than it's been any year, probably since 2005. And this hindered us quite a bit. And I'll try to explain to you, what we did to respond to those ice conditions and the data we were able to collect to hopefully answer the science questions that I'll lay out during the cruise or during the lecture. So the outline, this is what I'm going to tell you about. I'm going to talk about exploration, which is kind of a philosophical rumination. I'm going to tell you a little bit about plate tectonics. Plate tectonics is the ruling paradigm in geology and geophysics, and it's how we understand the surface of the Earth. With plate tectonics, geology advanced from a science of observation, of individual anecdotes, to a systematic science which had a basis for prediction. It was a huge change. And we're trying to apply, this cruise is very much based on trying to apply the principles of plate tectonics to the Arctic Ocean. The Arctic Ocean is not your grandfather's ocean basin, it's different. And I hope I can convey that to you. I'm going to talk about mapping the Arctic, which we've been doing in a succession of waves over the last 30-some years. Why this cruise on the Sikuliaq? I'm going to try and explain that too. What did we see? I mean, basically, this is the question everybody asks when you get back. It's what did you see? What did you learn? We're still in the process of examining the data we collected, but I have some tentative examples for you that maybe will be enlightening. And then the bottom line is, was the cruise a success? Well, in the Arctic, very often we go out and we have a plan. Plan A. That's what we want to do. But the plan A doesn't usually survive very long because we find conditions that prevent us from executing plan A. So we have plan B, plan C, plan D. And I think in this cruise we got down to about plan F before the end of the cruise. Basically, exploration. What is exploration? Well, you find something. It's an organized search. It's sort of paradoxically, it's a plan to find something you don't know. So you have a frame. You have a sort of an intellectual frame for what it is you want to learn. And I'll explain some of that as we advance. Geological exploration. Well, we look for resources. And based on reading I did before I started my PhD, I realized that there were two ways to make a mark in geology and geophysics. The first was to go someplace nobody had gone before. The Arctic Ocean, pretty good. Not a lot of people have been up there. The second was to make measurements no one has made before. And so basically what we want to do when we're exploring is we want to see what no one's seen. If you go to, say, the East Pacific Rise, which is a spreading ridge off Mexico, there have been 60 cruises to the East Pacific Rise, at least. And if to try and advance what's been done there, you're going to have to split somebody else's hair. But if you go to the Arctic, you can see things, you find things that nobody expects. I mean, what's better than that? To go out and be surprised. Now, plate tectonics is the basic paradigm for geology and geophysics. And what this proposes is that the Earth is covered by a set of rigid plates that are all moving relative to each other. We're forming new oceanic crust at the mid-Atlantic ridge. We're destroying oceanic crust under Mexico, South America, Japan, the Aleutians, and elsewhere in the basin. So what we're doing is that in the oceans, we're resurfacing the Earth. We're creating new oceanic crust. Wow, that's pretty cool. Now, this is a famous magnetic profile. In geophysics, what we very often do, we do things, we collect magnetic data, we collect gravity data. And magnetic data tells us about the total magnetic field. We can reduce that data, we can eliminate the ambient field, and we're left with magnetic anomalies. These are ways that the magnetic measurements surprise us. They're not what we expect. And these are magnetic anomalies from a mid-ocean ridge north of Antarctica. And what these are, if you squint at these a little bit, you start to see that they're symmetric. Here's the mid-ocean ridge right here. This is where new crust is being formed, where the ocean is getting wider. And what happens periodically over time is the Earth's poles flip. So if you have a compass and the poles flip, your needle points south instead of north. This is hugely important for geology. It gives us a tool to date, sediments, to date basalts, to date all kinds of things. And what you see as you move away from here is you see a record of magnetic reversals that goes back into time. Times when the poles were flipped, okay? And what we can do is we can create a map of seafloor ages. The dark lines here are the mid-ocean ridges. These are places where the ocean's getting wider. Over here, these darker areas, these are subduction zones. These are places where the oceanic crust is going down, beneath the continents, beneath the Aleutians. And what do we get from this? Well, the continents are old, billions of years. The continents are a residue that's accumulated through tectonic and geologic processes over billions of years. The oceans are young. The oldest oceanic crust is about 200 million years old, what maybe strikes you as old, but in geologic terms, that's actually quite young. So every point on the Earth's surface is in motion. Think about that for a minute. We're moving centimeters per year, but we are. People describe the accretion of oceanic crust as being something like the same rate as your fingernail grows, ranging from maybe 12 centimeters per year, imagine the two sides separating 12 centimeters per year, to less than a centimeter per year. And this is the important point, and this is why this talk, where we collected these data in the middle of the Arctic Ocean, is appropriate in a series called Science for Alaska. We did not understand the history of the continents until we understood the history of the adjacent oceans. Once you realize that the oceans are young, you can start to say, oh, well, that ocean wasn't there then. And this is the advantage we're deprived in the Arctic. In the Arctic, we've done everything backwards. Instead of understanding the ocean, we've stood on the edges of the ocean. We say, oh, this is that and that's that. Therefore, the ocean is this. Backwards, entirely backwards. And what I want to do is I want to change that. The objective of my research program is to change that. So now, when we understand the Arctic Ocean, when we understand its history of formation and modification over the years, we'll understand Alaska better. We'll understand northern Canada better. We'll understand Siberia better. That's what I want to do. Now, here's the International Bathymetric Chart of the Arctic Ocean. This is a community effort that's been put together by a guy named Martin Jacobson at the University of Stockholm. And the Arctic Ocean is divided into two basins. One is the Eurasia Basin, one is the Amerasia Basin. The Eurasia Basin is Cenozoic. So it's 58 million years, and it was formed when the Mid-Atlantic Ridge propagated north and cut this narrow sliver of continental crust right off the edge of Barents Shelf, starting about 58 million years ago. The Amerasia Basin, we believe, is entirely Mesozoic. Mesozoic being the age of the dinosaurs. So everything in the Amerasia Basin we think is young or older than 66 million years. Basic distinction in the history of the Arctic. There are other features in the basin. There's the Lomonosov Ridge, that sliver of continental crust. And one way you could think about Lomonosov Ridge is that it's like Baja California after 58 million years. There's a mid-ocean ridge propagating up through the Gulf of California, removing Baja California from North America. And after 58 million years, it might look like Lomonosov Ridge. Then we also have a Chukchi borderland, which we'll talk about at some length today. That was one of the primary objectives for the cruise. Mendeleev Ridge, Alpha Ridge, we won't talk about those much, and the Gackle Ridge, which is the slowest spreading ridge in the world ocean. Now, just to give you an idea, the first time I went to the Arctic was in 1993 on a US Navy submarine, the USS Pargo. We set sail with, it was a guy named Peter McCroy, who still lives here in town, from Connecticut, I can't think, Groton, Connecticut. And we're sailing along. And this is what I thought the Lomonosov Ridge looked like. It looks like, sort of a contoured hot dog. Now, when you look at these bathymetric maps, you should realize dark blue is deep water, light blue is shallower water. And the Lomonosov Ridge here gets up to about 1,200 or 1,000 meters. So I thought the Lomonosov Ridge, we're sailing along in the USS Pargo at about, 700 feet. And I'm talking to the quartermaster, and he says, when are we going to get to the Lomonosov Ridge? I said, well, it's going to be a couple hours. And he said, well, the bottom's coming up now. I said, oh. So this is, this is what we expected. This is what we found. So in terms of the location of the ridge, we were off by about, 100 kilometers or so. And in terms of depth, we're off by 1,000 meters. We don't know a lot about the Arctic Ocean, but this just slapped me in the face. Now, the story of this cruise is the ice gets in the way. This is a curve for the monthly Arctic sea ice extent going back to September 79 up to September 2021. You see, this has a pretty serious downward trend. And mostly my work has benefited from that trend, and I'll explain that as we go along. But this year it jumped up. This year, the ice retreated, but it retreated elsewhere. And so the ice was a substantial obstacle we had to deal with. Now, working in the ice has its own issues. Where we go, we want to collect data. We want to radiate sound and record the returns. And this is from the fantail of the US Coast Guard icebreaker Healy in 2005. With Yngve Kristofferson and John Hopper, we were collecting seismic reflection data. And as I'll explain, for seismic reflection data, you tow air guns and you tow a streamer. A streamer is just like a long string of microphones that record the returns from the air guns. The air gun's going boom, boom, and the streamer's recording the returns. But what happens is when the ice is compressed, it starts crowding in behind the ship. And when it does that, you lose the streamer. Now, when I've talked to oil industry people about this, when I say you lose the streamer, there's an audible gasp, because the streamer is 8 kilometers long and worth umpty $1 million. Ours was recycled streamer, so for us, the streamer was a consumable. That gets their attention when you tell them the streamer was a consumable. Now, I think you were in the waiting room and you saw video of Sikuliaq breaking ice. Icebreaker is a bit of a misnomer. Mostly they like to be ice avoiders, because breaking ice is expensive in fuel, and gee, you might scratch the paint. That's not good. But what Sikuliaq was doing in that video is it was backing and ramming. So Sikuliaq would advance into the ice, and because it's a low angle on the bow, it will climb up onto the ice and then crush the ice. And if the ice is resistant, then they have to back off and do it again. That's backing and ramming. Now, we're collecting multi-beam data while we're doing this, okay? So again, blue is deep, red is shallow. And each of these lines is a couple of pings of the multibeam. The multibeam collects a swath of bathymetry data, 4 times the water depth under the ship. So if everything's clean, we make this beautiful strip of map of the seafloor. But what happens when you're backing and ramming, you ride up on that ice, and I've been under Healy, and the transducers, which both make the sound and record the returns, have a little lip on them. And when they ride up on that ice, they back off, the ice sticks to the transducers, and it blocks them. And it stays there until the Healy is just going flat out. The ice gets swept off, and then you get a couple pings. Boom, boom, boom. So you make this map very slowly and painfully, these little strips of data at a time. So, you know, the story that I've been telling, and actually the story I told in the proposal, is that ice has been retreating in the Arctic, and a lot of the area I wanted to work I thought would be open water. Okay, so this is a great example. This is, there's a camera up on top of Healy that takes a picture like every minute. And this is from 2007. You know, you see continuous ice, melt pools, but continuous ice. Same location in 2012, 5 years later, about the same date, 100% open water. 100% open water. 2012 was an exceptional year. In 2012, the Western Arctic was open above 80 degrees north. And I was on the Coast Guard icebreaker Healy with Larry Mayer, and we were able to map that, living hell out of that. We could just do these long, straight lines, no problem. But this year the ice was different, and it was not quite as cooperative. And I thank Larry Mayer for this figure. So what was the ice like this year? This figure's a little complicated, but bear with me. And for all these figures, the orientation is north to the top. Down here at the bottom is Sikuliaq, formerly known as Barrow. Again, the deeper water is the darker blue, the shallower water is the lighter blue, even almost white. So I've plotted 3 important things on here. The thin yellow dashed lines are the position of the ice edge on September 15th, going back to 2015. Okay? And you see that on all of these, except 2020, there was, or in 2020, and this is 2018, there was some ice up in here. But the thick yellow dashed line is the average position of the ice edge from 2008 to 2020. And you can see the average position of the ice edge is way up on the northern Chukchi. This is the Chukchi borderland. The position of the ice edge on September 15th of this year is shown by this heavy red line. Now the ice edge is conventionally defined as 15% ice. So where we wanted to work was in here, up there, in here, and the ice complicated everything. We also wanted to tow gear. Towing in the ice is not a simple thing. You have to use specially prepared equipment, and you have to be prepared to damage that equipment. So this year, the ice was very different than it's been for the last 15 years or more. Very different. And it was more extensive. Now, this is the Amerasia Basin. I'm showing you 3 images of the Amerasia Basin. The first is bathymetry, and this is a little different. Here's the Mackenzie Delta over here, Banks Island, northern Alaska, Chukchi borderland. And I'm showing the 3 basic data sets that we use for marine geophysics. Bathymetry, the depth of the ocean, and again, the deeper water is blue, the shallower water is light. This is a gravity anomaly map. Now, gravity anomalies they tell you about the distribution of density. If you're near more mass, the gravity anomalies are high. And so bathymetry, you know, this bright anomaly here, that's at the shelf edge, the edge of the continental shelf. This bright area, that's the Chukchi borderland. So we can use this to track the distribution of density. Where's the dense stuff? We can use this to look into the seafloor a little bit. And then here is magnetic data. Again, it's a magnetic anomaly, it's a residue, but it tells us about the magnetization of the seafloor, and where we have high magnetic anomalies, we can believe that there's iron, there's basalt, there's volcanic rocks, there's igneous rocks. Now there are basically one model for the development of this Amerasia basin. And this is that the basin opened like a pair of scissors. Okay? So that northern Alaska, again, here's Point Barrow, and Siberia separated from northern Canada around a point, a rotational point, somewhere near the US-Canada border. It's a 66-degree rotation. The basic problem with this is this Chukchi borderland, because it stands high relative to the ocean basin, it's not oceanic, it's continental. That means it's thick. You know, when you have topography standing high, it's like floating on a root. And you can't just close this pair of scissors without doing something with the Chukchi borderland. That's the basic problem for all tectonic models, for all models of the development of the Amerasia basin. What do you do with the Chukchi borderland? So my research program has been focusing on looking at the edges of this borderland, looking for evidence of the structures that accommodated this motion. So now one thing that I should finish this first. One thing that we do see in the gravity data, plotted somewhat differently, is that there's what appears to be an extinct mid-ocean ridge in the basement below multiple kilometers of sediment. Now, if you look, remember that map I showed you, the magnetic anomaly, or the seafloor ages? Plate boundaries wrap around the Earth like the seams on a baseball. So we believe this is a mid-ocean ridge. I mean, what we can see beneath the sediments suggest it, the density anomalies suggest it, the magnetic anomalies support it, but we don't know where it goes up north of here. Plate boundaries don't just stop. They connect to other plate boundaries. That's how this motion across the Earth is continuous. So we wanted to figure out where this mid-ocean ridge went back in the Cretaceous or whenever it was active. So I've been taking a different approach to the Arctic Ocean. This idea that the Arctic Ocean opened like a pair of scissors dates back to a guy named Carey, who described the Arctic as what he called a sphenocasm. And he first published this theory in 1956, the year I was born. So everybody takes that, this opening like a pair of scissors is the right idea, and how do you fit all these other pieces in, okay? My point has been, I don't want to claim that the tectonics, that the opening was like a pair of scissors. I want to look at the features, the individual features in the basin, and instead of trying to jam them into some spatial model, see what they tell me about the history of the basin. And this is partly enabled by these newer, higher resolution gravity, magnetic, and bathymetry maps. I mean, when I sailed in 1993 on the USS Pargo, our hypothesis was about the location of the features. We didn't have enough detail to actually study the features. Now we have enough detail to study the features. We can look at their density. We can look at the bathymetry. The form of the bathymetry tells us about the history. We can look at the magnetics. The magnetics tells us more about the composition. So the basic objectives for this cruise were to look at the crustal structure of the northern Chukchi borderland, the extinct mid-ocean ridge, and what appears to be some adjacent extended continental crust. We want to understand the relationship between this continental Chukchi borderland and what appears to be oceanic crust in the Canada Basin. We wanted to track that mid-ocean ridge and figure out where it goes. It can't stop. Plate tectonics doesn't work that way. It has to connect up with another plate boundary. Where? And then we were also interested in contributing to the US mapping of the exclusive economic zone. Okay, so we're imaging the oceans, right? What we're doing is a variety of remote sensing. Mostly we use sound, okay? The frequency of the sound dictates what we can see. So if I'm using, say, a 30 kilohertz system, I can see the surface, the seafloor. If I take it down to lower frequencies, maybe 2 to 6 kilohertz, then the sound will penetrate 50, maybe 100 meters into the sediment, giving me an image of the sediments. If I can go down to 2 hertz, 2 cycles per second, between 2 and 200 hertz, that sound will penetrate kilometers into the ocean floor and give me an image of the stratigraphy and the structure with depth. And that's what I want to interpret. So the sound frequency tells us what we can see, but we measure time. It's hard to measure depth, so we measure time. We know when we transmitted the signal, we know when we got it back. That's called the two-way time. And if we understand the path that the sound took and the distribution of sound velocity along that path, then we can estimate depth. And we estimate depth from time. So this is a variety of remote sensing. And it just gives you a very basic idea of what narrow beam bottom sounding looks like. You know, you emit the sound, you return the sound. Now, the thing with swath mapping is, you know, typically when people did narrow beam bottom sounding, they just took the first arrival, the first return. But what happens is when you fire off that sonar, you have this expanding bubble of energy that returns an image bubble that, if you're smart, you can interpret in terms of a strip map across the ship's track. Okay, so we had a couple of acoustic sources on board. We had 2 air guns that were about 1,040 cubic inches total. We pumped them up to 2,000 PSI and we released them. And this gave us energy in the range 2 to 200 hertz. We used the swath bathymetric sonar from Königsberg. That was a 30 kilohertz sonar. And then we used the sub-bottom profiler that uses swept frequency signal between about 0.5 and 6 kilohertz. Now here's an air gun. These things are made of thick steel. And what you see here, this is the umbilical that goes back to it that has the electronic connections for firing and the pressure hoses to pump these things up to 2,000 PSI. Here's a close-up of the connections on the air gun itself. This is the rest of the portable MCS system. This is the streamer. We used about 200 meters of streamer, about 32 hydrophones. This is the connections for the air guns, containing air hoses and electrical connections. And these are the floats that kept the air guns at a particular depth. So here you'll see what it looks like. We're towing the air guns. You see the umbilical. There are the floats. And what you'll see is you'll see the float jerk, and then you see that bubble come up. That's when we fired the air guns. Okay? And that puts this wave, this pressure wave, sound wave, into the water that then encounters the seafloor and penetrates it to some depth. Now we use these air gun shots in 2 ways. The first is to collect what we call multi-channel seismic reflection data. And this is an example of data I collected in 2011 off the RV Langseth, which was not ice reinforced. And if you look, you can see all these layers. That's the stratigraphy of the basins that subdivide the Chukchi borderland. We can interpret these layers by looking at the reflection character and reflection continuity. We can determine something about the history of this basin. And what we determined in this case is that these basins were extended. These were pulled apart. And the sediments accumulated. A lot of sediments came straight down the axis of the Chukchi borderland from the Chukchi shelf. And so this is the track we sailed in red. Now, if you look, you can see that these tracks are kind of wavery and bumpy, right? That's because of the ice. We couldn't sail straight lines. We got to sail straight lines a couple different times. But we collected data in this area as a site survey for ocean drilling, in this area to image the Chukchi borderland. We did ocean bottom seismometer surveys in these two areas, and then we did a mid-ocean ridge survey on top of that extinct mid-ocean ridge. And here's the data we got. Okay, the red lines again are the ship tracks. Where they're highlighted in blue is where we actually got seismic reflection data. Now you remember I talked about going out in a non-ice reinforced vessel. The data I collected in 2011 was collected on this red grid. You see how straight those lines are? That was 100% open water. 100% open water. And you know, from when we first hit the basin in late August until we left in early October, that was 100% open water. But here, you look at these tracks that look like spaghetti that somebody dropped on a map. We were struggling in there. We were fighting. Now, one thing I wanted to mention from the previous slide that I forgot is the green lines are the lines I hope to sail. The red lines are the lines that we actually managed to sail. So I wanted to get further north, I wanted to get further west, didn't happen. I wanted to do these OBS surveys further north, didn't happen. The ice prevented us from going places I wanted to go, and it made the places we were able to get access to harder to get into. So we did a site survey, and you see these straight red lines. These are the lines from Langseth in 2011. And we put in a proposal to do drilling in the Arctic Ocean, scientific ocean drilling. And to do that, you need not just a single line, you need crossing lines, because they want to be able to look at two lines that cross and convince themselves that there's no oil and gas at depth. Okay, it's a safety issue. So we collected these data, but again, look at how convolute these tracks are. The ice in here was so thick that we just pulled up the MCS gear and went on to the next sites. Now, why is this important? Well, this is from some data we collected in 2005. And looking at the stratigraphy, there's a wealth of detail in here. You see that some of these layers are terminated and eroded, and you know, there's all kinds of stuff going on. But we don't have ages for any of it. And that applies to the data I showed you earlier that we collected in the Chukchi borderland. We don't know how old these sediments are. And without that, we have a hard time really interpreting the geologic history. Okay, we also looked at the Chukchi borderland. In the next figure, I'm going to show you an example of the multi-channel seismic data we collected right here. But again, you can see, you know, the green lines were what we wanted to sail. This was about Plan C. And these snotty lines are what we were able to sail. We got up in there, that was great, but I wanted to get way up in there. That didn't happen. That was just continuous ice. We couldn't, the Sikuliaq breaks ice, but it breaks ice up to about 1 meter thick. And if the ice is compressed at all, if the ice is in a squeeze, depending on how the wind's blowing, Sikuliaq can't cut that. And we certainly can't tow gear then. Now this is an example of the seismic reflection data that we were able to collect in the Chukchi borderland. You see some similar sort of patterns. You've got these basins again. And these data haven't been properly processed. This is just a very crude processing called a brute stack, where we just take the data, we combine it, and we look at what we've got. Now, I will say that given that we had to sail a very convoluted track, I'm pleased with the quality of the data, but we've got a lot of processing ahead of us to really make this truly useful data. Then we did ocean bottom seismometer surveys. At these points, we dropped ocean bottom seismometers, and they're just like seismographs that record earthquakes. And we sailed to them, around them. And here's an ocean bottom seismometer, right here. You drop them, they sink to the seafloor. They have this big cast iron bit at the bottom that gives them coupling into the seafloor. And then when you're done, you hit them with an acoustic signal. A wire burns out in the ocean bottom seismometer, and it releases the anchor. The thing rises to the surface. Now, these were in about 3,800 meters of water. So it takes about an hour for them to rise to the surface. And we were working in the ice there. Before we triggered them, we had to make sure that there was enough open water around where we thought they'd come up, that they wouldn't just whack on the ice and we wouldn't see them. So we had to do some waiting there. And then we had to do more waiting after we triggered them, hoping that they released and came to the surface. This is an example of an OBS record. The material, the returns in the middle are reflections, like seismic reflections. It's just instead of having a ship that's sailing, shooting guns, trailing a streamer, we have a fixed receiver and we're sailing around it. Now these parabola are reflections, but what we see out here, these are refractions. As you separate farther and farther, source and receiver, you pass what's called the critical angle. And then the energy isn't reflected, it's refracted, it's bent down. And it penetrates deeper. And this is what we want to see to try and understand the type of crust in the Canada Basin related to that extinct mid-ocean ridge. We did this survey on the extinct mid-ocean ridge. We did MCS. And we almost were able to sail straight lines here. It was pretty cool. Not quite, but almost. So our work is just beginning. These data will form the basis of a PhD thesis for a new PhD student, Visnu Priyantu. And Visnu came to start this cruise 3 weeks after he got married in Jakarta. And he came here and he sailed on the cruise and he spent fall term here. And they went home. He brought back his wife in January. And so far, she hasn't run away. So moving from the tropics to Fairbanks is pretty challenging. So right now, Visnu and I are in a conversation about how best to process these data. We had COVID challenges, doesn't everybody? We had to get Danish cruise participants on board. They needed visas, special visas, national interest exemption visas. We got them, but it was a struggle. We needed sea freight for 6 containers. When we were planning this, we thought the containers would be 7,000 each, Denmark to Anchorage, to Seward, not a problem. The price went up to 18,000, they couldn't guarantee delivery. That was a COVID problem. It was hard to get sufficient staff for the cruise. You know, people, I used to get people like from Norway or Germany or Japan or Korea, but they couldn't come. Students at UAF couldn't participate because the cruise straddled the first month of the fall term. So I really had to hustle to get people. And then we had a 1-week pre-cruise quarantine in Anchorage. That was the smoothest thing of all. Everybody made it through the quarantine. It takes a village to conduct a science cruise. Not just the people on the ship, but the people on the shore who support the ship and support the science. And I'll call out some of their names here in a second. A cruise also exists in an ecosystem. We're very aware that, you know, people, the native peoples up north refer to the Arctic Ocean as their garden. And we take a lot of precautions to make sure that we don't interfere with subsistence activities. We also take precautions to make sure we don't interfere with the marine mammals. And the precautions we took are all laid out here. This included, I mean, we also try to be very open. So I was sending out daily emails to members of the Alaska Eskimo Whaling Commission. We saw no whales in the area where we operated. Coming up through Bering Strait, sure, we saw whales. But we weren't, we had no active sonar at that time, no air guns. We only saw when we were actually active with the seismic reflection system, polar bears and seals, which was cool, but you know. And I think the reason there are no whales up there is there are no food resources for them. So the whales prefer to stay down south, closer to the shelf, where there actually is stuff to eat. Now, I have a long list of people to thank. First is the U.S. National Science Foundation, who funded the cruise. The second is, and Frank Rack is the hero of this cruise. Once we realized that sea freight wasn't going to work, we went to NSF and said, can we get military airlift? Because military airlift supports U.S. science in Antarctica and on Greenland. And Frank said, I don't know, we'll see. And it worked out. And so we got all the containers to Elmendorf Air Force Base just in time for them to be loaded on Sikuliaq and Seward and not hold up the cruise. We were lucky. If this had gone 1 week longer, the C-17s that they used to fly our sea freight containers were all in Kabul. So, you know, we had a narrow window and we made it work. Brian Van Pay, he helped us out with getting the national interest exemptions for the state, for the Danes to participate in the cruise. And Brian was very helpful with that. The crew of the Sikuliaq, you know, couldn't have done anything without them. The science party on board the Sikuliaq, which included some of my family members. The marine techs were outstanding, Ethan Roth, Steve Roberts, and Carmen Grado. And I owe immense thanks and a debt of huge gratitude to my good friend John Hopper, who handled the logistics from the Danish side. Just to give you an idea of how screwed up sea freight is, we offloaded the containers in Nome on October 1st. They may arrive in Denmark in about a week and a half. We hope. So John, I owe John a huge debt of gratitude. And also for operating the MCS and the OBS systems, the beneficiaries of Brian's help were Per Trinhammer, Lars Rasmussen, and Thomas Funk. Now, this is sort of a self-serving quote. And Harry Hess knew this, I think, when he said it. He was one of the giants of the early plate tectonics revolution. And he worked in US naval intelligence during World War II. He said, geologists make the best intelligence officers because they are accustomed to working with inaccurate, incomplete, and inconsistent data. Inaccurate, incomplete, and inconsistent. My job description. That's what we do. So sort of paradoxically, you know, exploration is an act of imagination. You believe something's there, you go. You find the means, you find the money, you find the ship, whatever, and you go. And sometimes you're just surprised beyond your wildest dreams. Thank you very much. That's the end of my story right now.
Professor Coakley, thanks very much. That, wow, a lot to digest there. Fabulous presentation. We do have some questions.
Oh, great. Okay.
But before we get into the questions, I do want to let you know about the reach that we have tonight. We've got somebody in Northeast Pennsylvania.
Oh.
We have Santa Rosa, California. We have Whitehorse, Yukon. A couple Alaska communities, of course, Juneau, Palmer, Homer, right here in Fairbanks, including some folks at Raven Landing, Valdez. And one other I noted here is from Dickinson, North Dakota, from Robert, who misses his old professor, Robert Ebelhar.
Oh, God. Bob.
All right. Let's see here. Actually, I'm going to kick off the question here, and I always like to do this, is why is it important we know about the Arctic Ocean and its history?
Well, as I said earlier, you know, every other place in the world, we've understood the ocean, and then the continent made sense. I mean, you've got the Appalachian Mountains, right? And they run up along the east coast of the US, and then they go dead offshore once you're up in Newfoundland. The Appalachians formed, say, between 500 and 250 million years ago. But once you realize that the ocean itself is like 200 million years old and younger, you can restore what those continents, where those continents were, and suddenly you realize, oh, the Appalachians continue into Norway. You know? So we don't have that opportunity to leverage our understanding of the oceans to improve our understanding of the continents that ring it. And I think that's very important. That's why I think this is a very appropriate talk for Science for Alaska.
A couple of folks, Helen and Sherry, in different questions here, are wondering about the impact of sonar on animals.
Yeah.
Well, maybe you could elaborate a little bit?
I agree with them. My problem, well, I won't say my problem. We live under a regulatory regime. And, you know, I can't prove to you that the acoustics don't change the behavior of whales. I believe that I can prove to you that the whales are not severely injured. But I will say further that where we were, there were no whales. There's no reason for the whales to be there. There's no food resources for them. I will also say that we're very careful to coordinate with the native communities in the northern shore, the North Slope, to make sure we don't interfere with their subsistence activities. We do our best to make sure that we do not harm marine mammals. And we adhere to the spirit and the letter of the Marine Mammal Protection Act. And we had six protected species observers on board. And they would tell us if we were not doing it right.
So you were out there well, everybody was out there for 6 or 7 weeks. And so this is a question about, for me, about life on the ship. Are you doing research 24/7? And how do you all get along? Yeah. And are you all good, close friends now?
Well, every science cruise is a psychology experiment. And there are successful experiments. And I think this was a successful experiment. Sometimes people get wound up and pissed off and, you know, trouble occurs about nothing. I take some steps to try and engineer a friendly situation, that people get along is very important. And we were working 4 hours on, 8 hours off, so 8 hours. I was working somewhat more than that. And, you know, the common reference point is the movie Groundhog Day, because every day seems very similar. You know, you see the same people, they say the same things sometimes, you know, which can get old.
Another question from a colleague here in the Geophysical Institute. Did your preliminary, and you might recognize who that is from the question here, did your preliminary seismic data support an old mid-oceanic ridge presence seen in gravity? What is an order of magnitude accumulation rate of the sediment in that area?
Ooh, it's hard to judge because, you know, these are turbidites. And, you know, turbidite deposition is intermittent. It's probably on the order of 1 to 10 centimeters per 1,000 years. At the moment, no data we collected disputes that this is an extinct mid-ocean ridge. And the gravity and the magnetics support that idea. But again, we really haven't had a chance to drill into it to really see what's going on.
And here's a follow-up question, I think. Can a seismic detection of layers be supplemented with the radar detection of sedimentary layers? And what radar frequency would you use for that?
None. Radar doesn't penetrate water.
Okay. So I guess the answer is 0.
It's 0.
Oh, okay, all right. Chronology of the sediment layers detected by seismic is a challenge. In 1964, there was a large earthquake near Anchorage. The ocean got murky from the suspended sediment from shaking. Does such quick suspension and sedimentation produce a potential layer for seismic/radar detection?
Yeah. Well, you know, there is evidence that turbidites, these density underflows, turbid water, that because sediment is held in suspension, it's denser than the overlying water, and it'll flow down slopes into the basin. Turbidites have been recognized as being triggered by earthquakes. I mean, the famous Grand Banks earthquake of, 1932 or something, that was studied by Bruce Hazen, and they had a whole series of cable breaks that occurred offshore. And from the timing of the cable breaks, they could estimate how fast this slurry of sediment was flowing down the slope. And the higher reaches of the slope, it was about 60 knots.
Another question here, going back, it's a follow-up to a question from earlier about sonar and marine life. Bridget wants to know, because you mentioned whales, and there were none up there, but she wants to know, oh wait, that's not Bridget, Sherry wanting to know about fish, the impact on fish.
As far as I know, I really don't know.
Okay.
The fish have swim bladders that probably resonate with the sonars. We didn't see dead fish in the water behind us. That's a fairly weak standard for non-harm. The oil industry collects these data in water that's much more biologically active than the water we were working in. And so far, I believe the only regulations are as far as marine mammals go. I don't think anybody's looked at fish or invertebrates or other smaller creatures.
Okay. This was a pretty international, I think, you had people from all over. Where did they come from and what institutions?
Well, everybody in the science party was US.
Were they? Okay.
Yeah, because we couldn't bring people from overseas. I mean, other times I've sailed with Germans, Koreans, Norwegians, and I like that. I actually like the opportunity to bring scientists together. But this year it didn't work out. This year I sailed with my wife, my 2 kids, a first cousin from Detroit, one of the father-in-law of one of my nieces, 2 students, one from Sonoma State, one from West Virginia, who were recommended by colleagues, one UAF student who had already graduated, so she didn't have to worry about fall term, a retired geophysicist from Exxon, who had been on the PhD committee for my previous PhD student. It was quite everybody got along and everybody worked together well, which is, what you want. But it was a hustle to recruit enough people to be able to do the work.
Here's a question from Jim. He says, our son Duke from Bethel, age 10, loves the lectures. He asks, you said the ship can only go through about 1 meter of ice. How do you measure the ice away from the ship? How do you know you're not going into ice that's thin and then gets thick? So how do you gauge that?
We don't. We look at the surface of the ice, and the ice doesn't vary in thickness over short spatial lengths. If we encounter ice we can't break, that's too thick. So we back off and we try somewhere else. The other thing we're looking for are ice ridges, where the ice is pushed together and piled up on itself, because Sikuliaq can't get through ice ridges. So we're trying to steer, like I said, they call them icebreakers, but they might better be called ice avoiders, because that's the easier way to go.
Ron Inouye asks, what technology needs development to help your research? What do you need?
What do I need? Wow. I don't know. The portable seismic system we used was good. It was appropriate for the application. I would say we need more capable vessels. Right now I'm on a committee that's evaluating how to build the next scientific ocean drilling ship. And that's not going to be a cheap thing. Sikuliaq cost NSF about $200 million. A drill ship is probably going to be up in the neighborhood of $500 million. And we need a drill ship that can access the Arctic and sample the sediments there. And this is not rocket science technology. This is building, a ship is just a different kind of tool, And some things you can do with it and some things you can't. And mostly I think what we need are smart applications of existing technology.
Okay. I remember in looking at some of the daily reports you sent while you were at sea about some of the repair work that had to be done on the equipment. Can you talk a little bit about the challenges and how that came about in fixing things?
You're dragging two air guns that are pumped up to 2,000 psi through the ice. The ice sometimes sweeps under the ship and comes through the propellers, and gets shot into the equipment. Sometimes, we've got two compressors going, and like all kinds of equipment, it will fail. And Lars and Per, our two Danish engineers, at one point, they just had to go to bed, because they'd been working almost 24 hours. It's not easy work. And so we shut down the seismic acquisition. I said, go to bed. The equipment takes a lot of wear in the water. And sometimes it just, like a couple times we had it work continuously for 24 hours. Hallelujah. Why? I don't know. But that was great. Other times it seemed it broke like every 20 minutes.
You carry spare parts?
It better be.
All right.
No, we didn't have any problem with spare parts.
Okay. Question here from a colleague at the GI. The ancient linear feature appears in gravity data as blue, and that usually suggests valley rather than a ridge. Is a deeper opening filled with the sediment your working hypothesis?
Well, remember the ridge, we call it a ridge, but the central portion of a mid-ocean ridge is typically the axis which is low. Basically you're pulling it apart, and if you look at most mid-ocean ridges, there's a central axis which is low, which is a valley. And what we can see in other seismic reflection data that's been collected across this extinct ridge is that there is a valley, and that's associated with the gravity anomaly.
Okay, we've got time for one or two more questions here, folks. I'm going to ask here, was there anything that you wanted to achieve that maybe didn't happen on this?
Yeah, I wanted to get up farther north.
Okay.
But that was 100% ice. We couldn't get there. We just couldn't. I mean, at one point, I think the captain staged an intervention because I was saying, no, we got to get up in there. And the captain said, hey, yeah, that ain't happening. The ship, I can't say enough good about the ship. They performed very admirably and tried to do everything I asked them to. But, ultimately the captain is responsible for the safety of the ship. I'm responsible for getting a good data set. And, if the captain says we can't do that, well, that's the end of the discussion.
And so folks can understand, how long does it take to bring an expedition like this about, from when you get the idea to planning, funding?
I submitted 3 proposals to NSF annually. Boom, boom, boom. The third one was funded. So that was 3 years. Then you have to get on the ship schedule. You know, the ship is available sometimes, not available other times. I mean, one of the things we discussed when it was looking very sketchy for the cruise to happen at all was postponing this cruise till 2023. The ship's already booked up for 2022. But I thought postponing the cruise till 2023, I had a huge time window by the stance of scientific research. And if I walked away from that, if I said, no, we'll postpone it, then Sikuliaq would have nothing to do for 45 days. Very antisocial in terms of my other Arctic seagoing colleagues. So, you know, I decided, you know, we're going to commit, we're going to try and make this happen. And we're very as I say, you know, I'd rather be lucky than good, and we were very lucky to get away from the dock and to be able to do as much as we did. The ice was, we got unlucky with the ice.
We have a question from Frank, who asks, what are the chances of actually conducting scientific drilling in the area?
What's the last name?
I don't have a last name, Frank.
Okay. Well, there have been, if you look at the history of scientific ocean drilling, they've sampled all the oceans. But there's only been one scientific drilling leg to the Arctic. It went to the central Lomonosov Ridge, not far from the North Pole, in 2004. This summer, there is supposed to be another scientific ocean drilling leg to the Lomonosov Ridge, but it goes farther over towards the Russian side. That'll be the second ever scientific ocean drilling leg to the Arctic. There's nothing to prevent us from working in the Arctic. It's expensive. You know, and that by itself is a problem. You know, we don't have infinite dollars and infinite time. The proposal that I made reference to that we collected the cross lines for, we've done a proposal to the Ocean Drilling Project 2 different times. But we face something of a problem in that, you know, to get funded, you have to tell people what you're going to find. And because we don't know the age of the sediments, there are some questions. So, you know, we can lay out, if you go somewhere in the Atlantic, you know, you're looking at some pile of sediments, you can lay out 10 hypotheses that you can test. In the Arctic, again, like before when we were sailing out, the hypothesis was, well, the features are here. In this case, the hypothesis is, we believe this is this. But nothing we've sampled within 2,000 kilometers can tell us any more about it. So, you know, it's a bit of a paradox. I think ocean drilling in the Arctic will happen one day. I think it's going to be after I retire, though. This cruise that's coming up this summer, I'm involved with it, but I'm involved with sampling the cores after they collect them in August.
All right, I think we're going to wrap it up here. I'm going to ask one last question, unless we get any in from our audience, our virtual audience. I'd like to know what's next for Professor Bernard Coakley. What else do you want to know about the Arctic Ocean?
Well,
that's separate from this most recent.
I'm working on a proposal with colleagues at Woods Hole and at Louisiana State and in China to go to the Gackle Ridge, which is the slowest spreading ridge in the world ocean. That's the ridge that propagated up from the mid-Atlantic ridge and separated the Lomonosov Ridge from the Barents Shelf. It's the slowest spreading ridge in the world ocean. And there was a dredging cruise up there in 2001 where they sampled volcanic rocks, which is what you typically get at a mid-ocean ridge, but they also sampled peridotites and gabbros. These are the rocks of the underlying mantle beneath the crust. So seafloor spreading has been going very, very slowly there, and it seems to have suppressed the production of melt. Now there are questions about how ridge segmentation arises, and ridge segmentation is expressed by variations of volcanic output, but also by what are called transform faults that offset sections of the spreading ridge. Gackel Ridge doesn't have any transform faults. It's just kind of the sinuous ridge. And I think that by working there, we might be able to figure out something important about how mid-ocean ridges are segmented.
All right, I think that's going to do it for us tonight. So
Okay.
thanks for your presentation.
Well, thanks. I thank everyone for showing up.